When Eigenvectors Fall Short, a mathematical thriller of dimensional constraints. In problem A19, we're tasked with find the eigenvalues and eigenvectors of the following matrix. M equals 1, 1, 0, 1. Can this matrix be diagonalized? Now, let's recall that last video was kind of all over the place, but the main summary there was suppose we had a matrix that when multiplied to a specific vector yielded a vector that was just a scalar multiple of itself. Hence, the linear transform or the transformation matrix, whatever you want to call it, multiplied to this specific vector, sent the vector to itself. This is known as the eigenvector. This is known as the eigenvalue as it's a scalar multiple. Now, the words eigenvalue and eigenvector are derived from the German word eigen, meaning own. So this matrix A maps this vector to itself or its own vector from some scalar multiple perspective for some vector that's not equal to the zero vector. Now, to find these things, we had to do some algebra to get this over to the left-hand side and factor that vector out, and then we see we're left with A minus lambda times I. Now, since x can't be a zero vector, we know that this has to be singular, meaning that its determinant must equal 0. So with that quick little refresher, if we want to find the eigenvalues, we must employ the equation A.19 and solve the characteristic polynomial. As such, we see that we have m minus lambda I, the M matrix here, the lambda times the identity matrix. Go ahead and distribute that in. Again, we know this is allowed thanks to the distributivity laws that we proved for vector space axioms. Now, when we take the difference of these two things, we do it component-wise, so we see that the lambdas stay on the main diagonal. Good to go. Now, just as a word of warning, this typically gets shortcut straight to this, so we don't have to do all this tedious work every time. But since we're trying to show those who haven't seen it before where it comes from, this kind of shortcut is going to be used all the time. Much like derivatives, you don't actually take, x squared, you bring the 2 down, then you take 2 minus 1, gives you just put 2x, right? So shorthand will take over at some point. Then when we take the determinant of this, we see that we have our vertical bars, and now we just have to take the determinant of this matrix and set it equal to 0. Taking the determinant gives us our characteristic polynomial. So A times D minus B times C. As you see, 1 times 0, that goes away, so we don't care about it. But what we're left with is a polynomial that's factored to 1 minus lambda squared, but all of it has to equal 0. So what we really are asking is, where does this inside equal 0? So 1 minus lambda. Clearly, lambda equals 1, but since the square right here, we know that it has a multiplicity of 2. So it's a repeated eigenvalue. Now, typically with repeated eigenvalues, especially in 2 by 2, this means that we're only going to have one eigenvector. So speaking of eigenvectors, to determine the eigenvectors, we substitute each of the two distinct, or in this case, the one distinct eigenvalue into the characteristic equation, which was seen in A.71 in the beginning. So this is our special vector, that is our eigenvector, and now we get to solve it. So we already did the matrix math on this, m minus lambda I, that was what was given here. Now we can plug in our eigenvalue, which in this case was just 1. So here we have 1 minus 1, that gets canceled. 1 minus 1, that gets canceled. So ultimately, we're left with a 0, 0 here. And what this means is that when we're multiplying this matrix into the components of this eigenvector, we still need to get 0. But this, as we see it here, this is a homogeneous system of linear equations, and we can solve it via Gaussian elimination. But this result is already in reduced form. So what we know is that taking this first row, multiplying it into this column, we get 0 times A1 plus 1 times A2, but all of that has to equal 0. Since this is 0 times A1, we're just left with A2 equals 0. That's very nice of us to have, but ultimately leads to something very bad when it comes to diagonalization. Now note that the second row being multiplied into this column gives us no new information because we just have 0 times A1, 0 times A2, and of course we know that equals 0. So we don't get any information from that. But since we know that A2 is this, we see that our V1 or A superscript 1 with these components, A2 goes to 0 thanks to this. So we can factor out the A1 from both terms. And here we see that this is a general solution of the form where we just have A1 outside. Here A1 once again is considered a free variable, and since any multiple of an eigenvector is an eigenvector, emphasis on the non-zero multiple though, we can set this variable to any non-zero scalar we would like. It's often easiest to use 1, so let A1 equal 1, and we're good to go. This means that by multiplying 1 into this vector, we just get the vector back. So for both the eigenvalues, lambda 1 equals 1, lambda 2 equals 1, which is the same as saying lambda equals 1 with multiplicity 2, as we see denoted there, we only get back one eigenvalue, or one eigenvector rather, that is normalized and is 1, 0. Okay, because all we care about in the eigenvectors really for the sake of quantum mechanics is the angle that it's at or the direction. So with that being said, we only have one eigenvector. That's not going to aim well for us when we want to diagonalize. So on the topic of diagonalization, a matrix is diagonalizable if and only if the sum of the dimensions of its eigenspace is equal to the size of the matrix. Okay, this is one way of saying that you need to have as many linearly independent eigenvectors as you do the dimension of the matrix or the size. For some n by n matrix, we should have n eigenvectors. Here, our matrix is 2 by 2, so we have a dimension of 2. And there's only one linearly independent eigenvector. As a result, since we don't have enough linearly independent eigenvectors to form a basis and actually span the space, the eigenvectors do not span the space, and thus the matrix cannot be diagonalizable. This is really sad to see, but ultimately, certain matrices aren't diagonalizable, which tell us about their solutions as well, but that would need a kind of deeper course in linear algebra, which of course is very beneficial to anybody who takes it. So another quick video, but one that kind of summarizes everything that wasn't as chaotic as the first video on eigenvalues and eigenvectors. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There is really so much more to uncover, and I'd love to have you along for the journey. I'd also like to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.